Okay, Assalamualaikum, afternoon. Let me just go to the notes straight away. We have gone through this 6, but we don't quite finish this as yet, if I can remember correctly. So let me just go down to the place where we stopped. I think we have done mentioning all these special methods, and probably we stop around here, essentially looking at functions of matrices. So one of the things that one could actually do is to take a power series for a particular function, and then and use that power series, replace the variable by the matrices, okay, and then essentially you have functions of matrices. The most common one being used inside physics is essentially your exponential. So I believe we have gone through this example of exponential km, where m was your previous matrix that was given earlier, this particular m. Are you seeing the cursor? Anyone? Or should I mark it? Somebody can respond because I can't see you. Okay, this is the m that we have gone through. Doesn't seem to be working. Just do this again. Okay, it's working now. So we have this m that has this periodic property, where the period is essentially 4, okay, until m to the power 4, and then when m to the power 4 give you identity matrix, when taken to the 5th power, it goes back to m. Okay, so essentially we talked about periodic matrices before this. We have defined this over here. Okay, so one could use those properties to actually simplify the expression for this exponential. Okay, so your matrices can be either your m. Okay, if you look at the expansion before the, or the powers before this, so you have m itself, m squared gives you minus I, m cubed gives you minus m, and m to the 4th gives you I. So it's either I or m. So in other words, one could collect all the terms that is proportional to I, and all the terms proportional to m. And essentially what's the coefficient in this particular case is the one that corresponding to this parameter k here. So it will be power series of your k, and one can immediately see that this power series are the one that correspond to your cos and the one that correspond to your sine. Okay, so in other words, what's there is cos k will multiply 1001, and sine k will multiply your m, which was given earlier there. Okay, so one could actually put all these things together, and essentially you're going to get this matrix as exponential km. A much more often used exponential of matrix in physics is given by the matrix itself is given by a Hermitian matrix, and let's recall what Hermitian means. Somebody want to say something? Okay, let's just recall what Hermitian means. You have your adjoint or your Hermitian conjugate, which is, remember, it was just simply the complex conjugate with the transpose. And if this is equal to M itself, then we call that as a Hermitian matrix. So one of the good things about this Hermitian matrix is when you take the exponential of Hermitian matrix with the multiplication of I there, there's an I there, I'm not sure it's visible to you, exponential I times the Hermitian matrix, that will immediately give you a unitary matrix. So essentially one can work this thing out. Your exponential is just given by that. Okay, remember there's an I, needs to take the power of n as well, together with your matrix M. And then if you take the adjoint, okay, the Hermitian conjugate, so you Hermitian conjugate the whole expression, the whole power series. Your I will turn into a complex conjugate. You get minus I over there. And your M dagger, now you can use the Hermitian property. M dagger is equals to M. So finally what you get is essentially this expression over power series of M, and that corresponds to the case of exponential minus Im. So then you can see that exponential Im times exponential minus Im is just going to give you identity. Okay, so this is your this unitary matrix. Well, we have not shown it to be unitary, but this is your matrix. Okay, and then multiply with this, which is just the inverse of that. Okay, so there you essentially get the unitarity property of the exponential Im. Okay. So these kind of things are going to be useful in quantum physics, so probably you'll see more of this much later on. So that's okay. The final thing is probably this about the general case is not going to be just like the one before. Here, for example, you have Im times exponential minus Im. So as if you take the addition of the exponents there, okay, and that gives you e to the power of naught, which is essentially this naught is actually your zero matrix. Okay, so this is zero matrix rather than the number zero, but exponential to the zero matrix give you the identity. So this seems to work because it's the matrix that appears in this exponential and the matrix that appears in this other exponential is the same matrix, your M. Generally, you have that simplicity. Your M and N would be different, for example, and then in other words, what happens in this particular case, the order of the multiplication matters. So this is not going to be equals to n times m, and that makes things a little bit more complicated, but people have tried to find an equivalent expansion for this. This is called Baker-Campbell-Hausdorff. By the way, I probably will give you some kind of self-study assignment where I give you some papers to look at and then you do a review. So this has to be done in groups, just like your assignment, but your group has to be a bit bigger. Maybe you have, instead of groups of 2, I will ask you to do in terms of groups of 4. Okay, well, this is for your SCL module. Okay. So this will expose to you some of the more interesting idea, which is not just a kind of exercise in a book kind of thing. You will see some applications of what you learn in this particular course to some research ideas. Okay, so hopefully I'll get to that. Okay. So that more or less finishes off lecture 6. Are there any questions at this stage? Please let me know, or give me a thinker or give me a ring or message saying that if I get disconnected. Okay, so I'm just not, I won't be able to see you at this point when I do the presentation. Okay, so now let me move on to the next lecture, which is lecture 7. So let me enlarge this a little bit. Okay, so the idea here, the idea here is to introduce the general concept of linearity. So the word linear will come quite a lot in both maths and physics, because that is going to be a very important concept we use in either maths or physics. Okay, so one particular case where you do have this concept of linear is a linear function. So you can consider, for example, a function of, say, a vector r. This could be something like this. Okay, your potential is a function of vector r. Okay, so that could be it, and in fact this will be the thing that you will see in quantum mechanics. Okay, and sometimes we want to change this r to a different r. One of the possibility is to have a vector addition. Okay, so in that particular case, one would like to see, okay, what would be the resultant potential looks like. Well, if it's a linear function, then it should obey this. Okay, so in other words, if you take the function of the addition of two vectors, then the linear function should give you the function of the individual vectors, and then you sum it up. Okay. Similarly, one could have another operation. This is addition of vectors. You probably also know there's a scalar multiplication with respect to vectors. Then over here you can just say that, okay, if you have that, let's suppose I have a equals to 2 instead for demonstration. Okay, so a is a scalar here, so I have f2r, which I can think of as fr plus r. Okay, but then according to this formula, then this will just be equals to fr plus fr, and that will be 2fr. Okay, so for integers like this, it will be easier to show this, but you can have a much general a here, where it could be a real number or a complex number, and this still essentially hold. Okay, so that is a linear function in general, and one could also test this idea. It's something that you have seen somewhere in physics. An example would be, okay, can I have something like this as a function of r, okay, where you have your r as being the variable, and then your a to be some possible other vectors that you might want to use. So it's a dot r, the scalar product of a and r is a function of r. Okay. Now we would like to test whether this function coming from this definition is linear or not. So one has to test it with respect to the vector addition property. Okay, so in this particular it works. Okay, so that gives us just a dot r1 plus a dot r2. What about scalar multiplication? It also works. So one might want to think, what kind of examples in physics can you think of that has this kind of property? Well, you can think of your work done. Your work done, essentially f dot ds. Okay, your ds here will carry off some variables of your position, for example. Okay, so we have all these properties that for which the linearity may help you to do calculations, rather than every time you see every time you have to evaluate the functions to a new vector, you can always express this as some linear combination of some vector. Usually one would prefer this, for example, if I were able to write any vector, for example, okay, later on we talk about basis plus vyj plus vzk, for example, then I can think of these individual terms as each one itself is a vector. Okay. I can think it that way, and I can now simply use the linearity to actually evaluate to any form of vectors. Okay, so that is one property that it could be useful, but one has to really check each time you see a new function whether you cannot just simply say that it's going to be linear function. An example is this. Example is this a dot r, okay, which is similar as the one above. Okay, but then you have an addition of this constant vector b. Now, what happens in this particular case, if I were to write down your gr1 plus gr1 plus r2, okay, by definition of this function, it's going to be a dot r1 plus r2 plus b. But this is not equals to gr1 plus gr2. Why? It's because of this term spoils it up. Okay, because your b, if I do this, for example, I have 2b instead of 1b. Okay, so that spoils the linearity. So usually for this type of problem, one take the difference between two functions. For example, I have another function that has this form of definition of the function itself. Then you take the difference between the two, where your constant vector becomes cancels out. Okay, so those are some tricks that one could actually do. But again, the lesson is to actually check the linearity property each time when you see a new function. Okay, now the function that we have just mentioned so far are functions where, let me just write this in terms of a map. So I take the function which is given by a vector, say in R3, and then this is the value of this function is going to be some scalar. Okay, so in other words, this is what we call a scalar valued function. But one could also have the more general possibility of a vector function. So in other words, this function takes a vector in R3, goes to a vector in R3. So this is no longer a scalar. Okay. So instead of one single number, it produces three different numbers. So in this case, this vector function is also linear. in a way that it follows the properties of the arguments. Okay. But again, as I said, every time you define these functions, whether it's the scalar value function or vector functions, one needs to check. Okay. And okay, so we have done linearity in terms of functions, but linearity goes beyond just functions. One could actually apply this to, say, operators. Okay, so operators over here is a nice example would be just your differentiation operator. So if you take differentiation on operator, x it onto some functions, okay, then you get a different function. So in other words, d dx, what does it do? It takes the space of functions. Tempted to put some symbol, but no, let me just write it down so that you can actually see what I mean, because symbols can be just can mean anything. So here your differentiation is just taking a function and map to a different function. Okay, so for example, f of x will get mapped to f dash x, your derivative. Okay, now this operator in itself is a linear operator. Why? Because if you take the operator acting on an addition of two functions, it's the same as the differential operator acting on the individual functions, and then you add it up. Similarly, if we take a scalar here, the scalar is usually a constant there. So again, then your scalar goes out from there, and then you have your derivative acting on your function f. So in other words, this is what we call a linear operator. And you can check that any higher order derivatives will be also linear. Okay, these are linear operators. What is not going to be linear? So operators are what? Operators are things that take the space of functions and map to another space of functions. So if I were to do this, for example, I take d dx and take, say, operate on this f, and I square it, and I call this operation to be, say, square of f. Okay, or something, okay, whatever symbol that you want to use. Okay, so then this square is not a linear operator. You can check that for yourself. Okay. So in this particular case, one can almost immediately see that, okay, if it's the derivative standing on its own, then it's fine. But you start to couple your derivative with some other things like the square or cube or some power, okay, then you have problems. Okay. Right. So generally, one could now talk about a much more general operator in a way. So if it obeys this, okay, it obeys this property with respect to the addition of functions or addition of whatever objects there are supposed to be in this argument of the operator, then and also this scalar multiplication, if it obeys this, then we say it's a linear operator. And linear operators are the things that people use in quantum mechanics. Okay. Okay. Now another thing that you have actually learned is your rotation matrix. Okay. So rotation matrix will act on a vector. Okay. This is the vector. Now one could ask, okay, if your external vector, just like your function before, okay, you have a function f r, for example, previously, but now instead of making this as a function, you have a matrix multiplying the vector. Well, it so happens that this operation of a matrix multiplying the vector here is a linear operation. Okay, so I can take, for example, the addition of two vectors over here. So I have x1 plus x2 for the x component, y1 plus y2 for the y component, and then I'll do the rotation matrix onto this vectors there, and then I can similarly sort of decompose the answer into this form, and I will be able to get it in this particular form, which is precisely the thing that you need for the definition of a linear operator. Okay, so in other words, rotation metrics are going to be linear operations. This is quite simple for you to check. Okay, this is just your scalar multiplication. So, so there are many things that one could actually associate with this idea of linearity. Okay, so generally, one talks about linear maps. Okay, so going from we started off with functions. Okay, which could, okay, let me just write it down. First, we had functions. And there are two types of function. One that goes from R3 goes to R, and then R3 goes to R3. This is a vector function. And then you have something like your, what was that earlier, space of function to space of functions. Okay. So we have generalized this idea of linearity with respect to all these different maps. And I've said it. Okay, it's a map. Okay, so one could consider the space of, the idea of linear maps in general. So I may want to generalize this is what we call the domain. This is what we call the range, or sometimes we want to use codomain. Okay. Then I can generalize the idea of domain and codomain, and I'll be able to talk about linear maps in general. Okay, so over here, usually we'll take a vector space here to another vector space here, for example. Okay, so then this linear map of f, okay, whatever this operation is supposed to be, and obeys this particular what you call properties, then essentially this generalizes the idea of linear operators on V. Okay, so there are other things which will be, you probably learn this later on. There are things also called linear functionals. Linear functionals are the cases where your maps, your codomain of the maps, are going to be the space of the real numbers or the space of the complex numbers. Okay. Have you done quantum mechanics? Let me just check if there are anyone who has actually done quantum mechanics. Anyone? Say yes or no. Yes? Yes or no? No, okay, no, okay. So in quantum mechanics, you'll be getting the idea of a dual of a vector. Okay, a dual of a vector, is essentially a linear function. But okay, I mean, you might get this a bit too abstract for you. Probably later on, when you see how to do calculations on this, probably it will be much easier. Okay, so it's at the moment these are just concepts that you're supposed to get familiar with. Okay, right. Generally, the kind of space of linear things, okay, are called linear spaces. I can talk about space of matrices like rotation matrices just now. So they are linear maps, okay, going from say R3 goes to R3. So the space of rotation matrices are part of what we call the linear spaces. And linear spaces, they have a more common name as vector spaces. So again, this is something that, okay, you might want to say that the way I learn vectors are just a vector in R3, okay, but it can be generalized, okay, can be generalized beyond this R3 that you always learn about vectors, okay. So this could be, higher dimensional things. So there will be some basis, and we'll talk about basis later on. So there must be some rules for which this what belongs to a particular vector space. Well, you have not done linear algebra in maths. Probably this will probably be new to you, but again, it's just a generalization. Okay? The gist of these ideas are just, you take a familiar idea that you have seen before, you generalize it as much as you can. Okay? So over here, so there will be, in any linear space or in any vector space, okay, you have a set of elements to the vector space. So the vector space here is labeled by capital V, and there will be two defined what you call operations. The one that we have seen before is the vector addition, and then the other one is scalar multiplication. So in other words, you need also to define what scalars are going to use. Okay. For example, if the scalars are just simply R, then we say that this is a vector space over vector. I cannot spell space. What am I doing? Vector space over R. Okay, if your space of scalars are just real numbers. But if your space of scalars are complex numbers, then we say vector space over complex numbers, over C. One could, in fact, generalize this idea of R and C, but I will not go into that because that might cause some confusion, but there are other things besides your real numbers and C to be your scalars. So you can define a vector space over some more general, what we call field. So the field in maths is not like the field in physics. The field in maths are those that obey certain properties, which I will not say out here. You probably learn this in much more advanced courses, but essentially R and C is one of them. Okay. Okay. What else do we? You have to implement certain rules. When you generalize things, you might fall into a problem where your earlier rules that you assume might not work. Okay, so that's why one need to specify what the rules are. These are things that you also see in the abstract quantum mechanics. Helps you you learn later on. Okay, is that when you do vector addition, the vector addition is commutative, so you can swap the addition around. So, and then it's associative. So if you know how to add two vectors, you should be able to know how to add three vectors. And then you have a null vector. Okay, null vector is sometimes called the additive identity. And then once you have an additive identity, you should have an inverse. So your inverse are given by the negative of the vector itself. So that gives you, not this one. This one. So this is additive inverse. And then with respect to scalar multiplication, you have this compatibility of scalar multiplication, because you can multiply between scalars, and how the composite scalar multiplied a vector is the same as consecutive multiplication of scalar to the vector itself. Okay, so compatibility of scalar multiplication must be there. Then you need to have a scalar identity, so that when it multiplies the vector v, it gives you v. And then once you have these two operations together, then you should be able to do a composite operation, meaning you combine two different operations together. So here is an addition, here is a scalar multiplication, so you should be able to know how to combine those two, and that gives you this rule. And of course, you can also combine your scalars, not just multiply them. You can combine your scalars through addition, because you have also addition and multiplication. So this is again, this is related to the concept of field. So you have these two operations that you need to define a field. Okay, so you have this scalar added together and multiplies the vector v, and how it should behave like. Okay, so these are some rules so that you are able to generalize the idea of a vector to a much more general vector space. Okay, and given a vector space, there is a natural sort of structure that comes with it, called the basis vectors. Okay, so this is going to be, I'm going to skip some of this because you don't need all of this. So the idea of a vector space always comes equipped with a basis vector. So you can always find the set of vectors which are forming the basis. And what's required of the basis, it needs to be linearly independent. So if you have not seen this before, I hope you just take this definition, will be enough. You take the linear combinations of linear independent vectors, and suddenly you add it up to equals to the null vector, then the only solution for that is that all your coefficients here will have to be 0. Okay. So, and then what else? It has to, okay, linear independent is one property of basis, the other one is spanning. Okay. Oops, where did I go? So the idea of spanning is the fact that one can always append to this set of linearly independent vectors, so that one would be able to express any vector inside the space using a linear combination of the basis vector. So that's basically it. So I do not want to go too much into the details here. So finally, you take any vector v inside your vector space, v, capital V, okay? Then you can always decompose it in terms of linear combinations of your basis vectors. And your zero vector, for example, your decomposition with respect to the basis is always that you have all the coefficients to be 0. Okay. So let's go through some what you call slightly different example that probably you have not quite seen. An example here is the standard example in the case of R3 here is to have your ijk basis. But you could have also something else like this E plus, which takes this I plus I addition with J and an E minus with I minus J. And this is also a set of linearly independent vectors. So I can write, instead of this ijk, I will have E plus E minus nk. And you can check for yourself that these are linearly independent. So in other words, it forms basis. Okay, and you can also check that it has this spanning property. Okay, so these are all going to be important when you start doing generalization and things like that. Okay, so we'll talk about, I think probably later on, when you go to transformation of matrices, sometimes you need this kind of different bases. An easy example would be this. Okay, you have your Cartesian coordinate, you have this basis. Okay, suddenly you change coordinate system, then you have a different basis. So this is a basis in, say, polar coordinates. Okay, where each of these could be a linear combinations of your ijk. Okay. All right, so I think let us take a break at this stage before we move on. Is that okay? Anyone wants to continue? So we'll take a break now, okay? Okay, is everyone back?
Yes, doctor.
All right. Let me just continue with some ideas. I can't precisely remember whether these are actually taught in Boas or not, but I do remember bits and pieces of what she did includes these ideas. So here what we're going to do is to generalize some of the things that we already know in vectors. For example, one of the things that we already know in vectors are essentially your dot product. Okay, your dot product in ordinary vectors space can be generalized to the idea of an inner product. It has the same symbol usually, but the idea is now can be generalized to any dimensions and any types of vector space, including the complex vector space might have a bit more different definition. But the idea is you can generalize your inner product, which is a generalization of your dot product or scalar product. Okay, the idea is still the same. You combine two different vectors. You take two different vectors in the space, and you map this to, in this case, your scalars, which will be the for the real vector space will be the real numbers. Okay, so this is essentially your inner product. Okay, so from inner product, from your dot product, you also have learned something else. One of the things that we have learned is the fact that you take the dot product between two ordinary vectors, and it gives you 0, then using the definition that we have seen in school, which is really a geometric definition, your cos theta, if I'm not mistaken, right? Cos theta, and if this is 0, that means your theta is pi over 2. Okay, and that defines orthogonality. So we do the same thing here. Okay, despite that this is now in higher dimensions, besides 3, one can still define the idea of orthogonality, okay, by saying that you take the inner product between two vectors, it will actually give you 0, then your two vectors are orthogonal. We also have this idea of a length. So you take the ordinary vectors, this becomes vx squared plus vy squared plus vz squared, and then you take the square root, that gives the length. We also have the same thing here. So here is, sorry, this is square root. So the magnitude or the length of the vector is that, sorry. Okay. So the same thing happens over here. So instead of a dot product, this is now an inner product. Okay. And one can always divide a vector by its, so this is sometimes called the length, length of v, which is actually the norm in a much more technical language of maths, the norm of v. And one can always normalize your vector v so that the norm is always unit by just doing this. You take the vector itself. Okay, sorry, I should now have a different symbol for that. Okay, maybe I use that hat thing. Okay, it's also being used in Boas, I think. So you have this unit vector v is really defined as the vector v divided by the norm. Okay, so you can actually get the norm of that unit vector is always equals to 1. And you can check this for your basis. No, okay, sorry. Your bases are normally assumed to be of unit length, okay, but it's not necessary. But a standard thing to do is to take that your basis to have unit norm, and all your different basis vectors are mutually orthogonal to each other. So then we see that these bases are said to be orthonormal. Okay, orthonormal means orthogonal, okay, plus being normal. So generally you have this again, the appearance of Kronecker delta. So this is particularly useful when you go to the index notation. Then you have this ei dot ej being orthonormal here. So if it's the same, then I have delta I, for example, or delta 1, 1 as an example. I equals to 1, j equals to 1. Then I have equals to 1. If it's different, say delta 1, 2, then it will be equal to 0. So that means it's orthogonal. And the practicality of this orthogonality thing, then you can always simplify your calculations over here, which reduce to the thing that you have seen for your inner product. The other useful thing about orthonormal basis is that you can, given a particular vector v, see, you can always find the components of v. That means you have first component, second component, by just taking the inner product of the basis vector, which is now assumed to be orthonormal. Okay, dot inner product with the vector v itself. The definition of scalar product and inner product has the same geometric meaning. What does it do? It projects. For example, you take this vector v, it projects down to a particular direction. Okay, and this will be your theta then, your cos theta, for example, in your v dot w thing. Okay, so this So this is a W, so this is V dot W will be, say parallel to this W direction. Okay. And what else that one can actually prove? Again, I'm not going to go into details, but these are things that you probably need to use at some time in the future. Is the idea of Cauchy-Schwarz inequality. Okay. The magnitude of your V dot W is always less than equals to the product of your length of your V and length of your W. So these are called Cauchy-Schwarz inequality. Okay, maybe forgotten this. Probably this is just Schwarz inequality. Okay. Cauchy-Schwarz inequality might be something else. I can't remember. Okay, but anyway, but you have this this condition being less than that. Okay, so that's important. This one I'm not going to go through. This is again just some proof, and then the idea of Gram-Schmidt process is given a set of vectors in a vector space. You can always try to find basis, and the basis can be obtained through this process called Gram-Schmidt process. All you need is to sample some vectors from the space, and then you start doing these particular steps, which I will not go through, and then you'll be able to define an orthonormal basis. Okay, so for us it's sufficient, I think, just to be able to use the concept of orthonormal basis. So that's probably that. Oh, okay, this is going to be important. What's the remember I mentioned about your inner product being generalization of a dot product in much more higher dimensional space, and then I mumbled something about complex vector space. The definition of inner product in a complex vector space is going to be slightly different from the one in the real vector space. One of the vectors, in order to have an inner product, one of the vectors has to be turned into a complex conjugate. Okay. The idea is why you need to do this is that from the inner product, so this is inner product in complex vector space, you're always able to define the norm. And what's the norm? The norm is coming from the inner product of the vector with itself. So if this is not to be given by the complex conjugate, what's going to be? Then it's just vi, where vi could be a complex number. So this whole thing might be a complex number. Somebody in contact? Okay. So this will not work for the case of the complex vector space, so you need the conjugate. Because once you have the conjugate, sorry about that, some other device there. So when this is a complex number, then when you multiply with the conjugate, then this becomes a real number. And that's what you need for the norm. Okay, but your norm sort of gives the length. The length is given by a real number. So that's why you need a slightly different definition for the case of inner product with a complex vector space. Okay. So I think the rest should be easy to follow. Okay. Now we're going to generalize this much more than you probably would want to hear in some sense. Remember we had functions being linear, right? So in other words, if functions being linear seems to have these properties of a vector, you have this scalar multiplication together with vector addition. So a possibility is to consider a much more general idea of a vector space which is going to be infinite dimension. Now, this might come as a surprise to you, but space of functions like the one I mentioned just now could be, okay, it's not necessary, okay, could be a vector space. Okay, could be a vector space. So one of the properties that you need is essentially your vector addition thing and then your scalar multiplication, but you also need something to control this very large space of functions. One of the things that normally is needed is the idea of a basis function. Okay, just like your vector space has basis vectors. Okay, now for vector space of functions that behaves linearly, okay, one also needs the idea of a basis functions. So what are basis functions? Basis functions are those that comes from a linearly independent set. So how do you know whether a function is a linearly independent set? Well, one of the things that we can actually know if the functions are linearly dependent. Okay, it gives you the same definition as before. The coefficients multiplying the functions themselves has to be 0 when it adds up to 0. But there must be a better way of trying to find whether a set of functions to be linearly independent. There is, okay. So there is this idea of a Wronskian. So the theory behind this is a bit more complicated. So here we just learn how to use it rather than learn the theory itself. So you have a set of functions, and this can be linearly dependent. Then one could actually the assumption here is you need to be able. So if you have n functions, you need to be able to find the derivatives up to order n minus 1 in order to be able to see whether each of these functions are going to be linearly independent or not. Okay. Now, how do you do this? Is to use this Wronskian, which is really a determinant. Okay, the determinant of the set of functions together with the derivatives. Okay, so in a way, what is this saying? So I can immediately from the properties of the what you call determinant, if any one of these functions is actually the same, then I will what you call automatically get 0. Okay, that's one. But you don't only need that, you need also to check your derivatives. Okay, so I can have something like this. You have a function that looks what should I say? That looks the same at the level of the function itself in certain what you call certain domain, certain what you call certain interval of your x, but okay, it might coincide with this. The function can coincide with this in this interval, okay, but your derivatives are not, so they are still considered different. Okay, so there one has to do this until you are able to find the derivatives. If you are comparing n different functions, you need to go up to the n minus 1 derivatives to check that each of these derivatives are not the same. Okay, if they are not the same, then this Wronskian will not be equal to 0. If they are the same, that means if you find even one of the derivatives are going to be the same between one function to the other, then these are going to be linearly dependent. Linearly dependent. Okay? So this is a thing. The theory is a bit more complicated in this particular case, so we are not going through, but we need to be able to use it to define the set of linearly independent functions. So one of the things that you probably have seen, I think hopefully we have enough time this semester to go to Fourier series. Fourier series is to say that you can expand any periodic function with this set of basis function. One, which is essentially your constant function, and then cos nx, sin nx. This would be considered as a complete basis for your set of periodic functions, and n here can be varying from 1 to 3 and so on. Okay? Actually, you can go from -1 as well, okay? But there will be some symmetry properties. Okay, so those we need just to know how to define it. Again, the idea here, you are generalizing the concept of vector spaces to space of functions. Okay, so you need those concepts to check things out. The next thing, I think I'm following Boas. We are going back to simpler things, which I was thinking is a bit repetitive in a way, but let me just mention this. Okay, you go back to Euclidean space, particularly in R3. That means you can always find this I, J, K as your basis vectors, and then you go back to the original vector algebra and vector calculus. Well, we are not doing calculus at the moment, but most of the vector algebra will be there. But here I want to highlight two different approaches to vectors. Okay, one approach is to be algebraic. Okay, so the algebraic approach is to decompose things into components. And then once you decompose into components, then you can use those components to do manipulation and calculation and things like that. And for that, it's easier to do calculations with the algebraic way of approaching vectors. Okay, that means you always write down in terms of components like we have seen over here. Okay. But a much more geometric, okay, so the other one will be geometric, which is less dependent on your components. Okay, let me just mention why one needs to have these two different versions. The component is good for calculations, but one of the problems that comes with component, this depends on coordinate systems. Okay, so the geometric way of approaching vectors is to use the relationship between vectors rather than breaking it down into components. Okay, so one of the things that we already learned, for example, probably this used to be taught in high school, or at least I remember at the time in STPM or matriculation. Okay, we are taught about this. This is called the Paragram Law, where what happens is that the Paragram Law is essentially a geometric way to define the commutativity of your vector addition. Okay, so that means A plus B equals to B plus A. And this is understood in this particular context. You can talk about A plus B this way or B plus A this way. It gives you the same diagonal of this parallelogram. Okay, so that is much more geometric. So in other words, this property is coming from this geometric property of the parallelogram. Okay, and you can have more. No, you talk about associativity. You can actually draw diagrams for associativity, but it gets more complicated. So your geometric, okay, it's good to have a holistic picture of what's going on, but it can get complicated when it comes to calculations. Okay, so I'm going to skip all those. Okay, so most of the time we use, this is the algebraic one. For example, this is for the case of the dot product, or generally it's inner product. This is what we call the geometric one. Why is this geometric? Because it talks about the length of this vector A, the length of this vector B, and the angle between vector A and B. Okay, so these are things that you draw usually. Okay. What else I want to do? Okay, this is also important. So for example, when this is nice in a way that okay, how shall I say this? Probably I should mention just this. Okay, when you find that your A and B are parallel, the idea of parallel is actually a geometric thing. What one can actually deduce is, you can deduce something much more than that. That means when it's parallel, it's actually proportional to each other. That means you can actually find a scalar here for which that scalar becomes the constant of proportionality. And from that, you can also say that, okay, I have these properties within the components themselves to be equally. Okay? So these are things that probably is a bit it's nice to have some kind of imagination that we are able to see these properties as a diagram rather than as a algebraic formula. Okay, so that's what I'm trying to say. So again, cross product, you have this as your geometric case. And in terms of component becomes that, which is, this looks horrible now. Even though it's easy to calculate, it becomes horrible when you write them down in this way. But now I'm going to teach you something slightly different. So this is what, again, these are some geometric explanation of all the vector operations. I think you can just read. Now, in order for you to learn something extra beyond what you already known for vectors, I'm going to introduce, just like before, the idea of index notation. Okay, the idea of index notation is convenient because you can start to prove general formulas. So you don't need to limit yourself to vectors with numbers in it, but you can just manipulate algebraically. So what do we need in this particular case is to introduce what we call, again, please, if you are in the other group, don't use this. I don't think it was explained in the other group because it's just that I tend to give extra things to you so that when you go to other courses, it might crop up again, particularly when you go to theoretical physics courses. One of the things that I use over here, for example, when I teach special relativity, which is going to be offered next semester. So, I use this Einstein summation convention. Okay, let me just tell you what it is. Okay, the Einstein summation convention is to observe the fact that when you do summation, for example, here to show the decomposition of the vector v itself, okay, you sum over the components of each vector together with the direction, right? This gives you the direction, this gives you the components. Okay, and this is sum over I. Now I could have written it with a different index. For example, sum over Vj, and then this is going 1, 2, 3 again. It's the same thing. It's the same thing. Nothing is actually different from this, apart from you use a different symbol. So in other words, this symbol, which is stuck within this summation, okay, it's the same symbol for both objects, okay. And what Einstein tries to simplify the notation is to, okay, if I want to sum, I just use two same index. Okay, when I see these two same index, I and I here, it means I'm going to sum over I. And this I is called a dummy index. Why? Because I can replace this dummy index by any other index. It means the same thing. Vjej is the same thing as Viei. Okay, so these are some. No, it sounds complicated, but you'll see why this is going to be useful. Okay, so here is an index notation for addition, index notation for scalar multiplication. The only thing that you need to be careful, because you attach the meaning of repeated index, the dummy index being repeated, okay, with the sum, you need to make sure that every term in your what you call appearing in your expression will not have more than two repeated index. If I have three repeated index, then I will not be able to know which pair is going to be summed. So these are some rules. And then the other rules is essentially the unsummed index is called a free index. And the free index carries the meaning of you're looking at a particular component. So if I have an expression over here with index I, then on the right hand side it must have the same I as well. So this is sometimes called free index are conserved for both sides of the equation. Why it has to be conserved? If I talk about v plus w, the x component, then it has to come from the x component of v and the x component of w. It cannot be anything else. Okay, so in other words, that I, that free index, needs to be conserved. Dummy index, you can replace it. Okay, can be replaced. So there are a few things over here. Okay, the Kronecker delta, I think I mentioned at some point, I can't remember when precisely. The Kronecker delta is related to your dot product or inner product, and then your cross product is related to your epsilon ijk. This is the Levi-Civita symbol. As I believe I have done this, right? Can somebody confirm this with me? Because I seem to be, deja vu kind of feeling that I've done that all. Anyone? or is it from the previous semester? I'm not sure. I think I have, at least in the determinant when we talk about the determinant, right? So we have introduced Levi-Civita symbol. Here the Levi-Civita symbol is also related to determinant, if you see what I'm saying, because you have this determinant of V cross W. But now what happens over here, your epsilon ijk is now associated with your cross product. For example, over here, okay, here's a nice demonstration of this thing. So I have this V cross W, the I component. So I have a free index over here. And that means on the right hand side, I should have a free index I. But here I have also the other index G and K, and they are dummy index. G repeated here and here, K repeated here and here. And this sum of our J and Q, so this is really means what? J and K being summed from 1 to 3, epsilon I j k v j w k. So that is what it really means. Okay. And one of the key thing with this epsilon thing, it obeys this relationship. If I take the product of two epsilons, is equivalent to the determinant of your Kronecker delta. Okay? Particularly if there is something like this. I have a product of two epsilons over here, but you see there's an index I on the first epsilon and index I on the second epsilon. So this is like taking a dummy index. That means there's a sum over I over there, and this is equal to the product of these two deltas, and you can actually prove this formula from that formula. Okay. Now, why is this important? Is when you have things like this. When you have, let's say you want to see this triple cross product. Okay. And you know how cumbersome this is if you want to try to prove this. I think you probably learn it in terms of A, B cross C, and then this becomes, is that right? So B, come on, U, V. So this is, getting confused myself. So U is A, V is B, C is W. So U dot W times V here is, so I should have B A dot C minus C A dot B. Right? So this is the back cap rule that you probably have learned somewhere. Okay. Now you know how lengthy to prove this, because you are not given with numbers. Your A are not, no, there are no numbers inside A, there's no numbers inside B and C, and you are all given symbols, and to expand this triple cross product, you can, you have at least one page of algebra that you need to do. But with the index notation and with this identity, for example, you are able to use this much of proof. How many lines? 1, 2, 3, 4, 5. I think the next page is 6. Okay. 6 lines. Instead of expanding your determinant so many times. Okay. So that's the utility of this index notation. Okay. So if you need to prove a vector identity in a sort of abstract form, meaning you are not given numbers, then you have to use, well, not you have to use, it's better to use index notation. So I'm just giving you all these tiny details are usually not given inside boards. Okay. So probably this is the best place to stop. Yeah, because we go, otherwise we go to the next lecture. Should we go to the next lecture or should we stop? I'll let you have a say because we have missed one lecture, 1 2-hour lecture there on the previous Monday. Should we continue? Are you still with me or I'm disconnected from you or what? Nobody seems to be saying anything. Should we continue or we wait for the next lecture? I'll let you have a say on this because I feel tired as well. Next lecture, okay, great. Okay, so we'll stop for today. So let me just take your attendance first before we leave. Please do discuss about replacing the lecture because I think no, because I promised to. Okay. So the attendance taken. So I think that's all for today. So thank you everyone. So I will stop the meeting now. Okay, bye.